still underneath chemical changes, believe it or not. Okay, even though it's taken us about a week or more working on this stuff, we're still underneath chemical and physical changes. You know, if you go back probably to last Tuesday or something when we first started this, because then when we talked about it first, about physical versus chemical changes, then we concentrated on chemical changes, which you just did a lab on, obviously. Just keep them doing that. All right. And when we talked about chemical changes, what did we say? Well, first we had the definition and explain what one was, and I hope you guys got those right back there for determining whether they're physical or chemical. But there will be mistakes. I just graded some of the earlier periods, and there are mistakes on that, believe it or not. Actually, quite a few. But then we talked about how you would know it. Underneath that, number one, this is 4 underneath chemical changes. Number 1 was evidence of chemical change. Just use that through that lab. You should have been using and writing down stuff like a gas was released, or a precipitate was formed, or there was a color change. Things like that, or heat, light, electricity, something like that was given off. Those are the things I told you to look for. Those are the things you should have written down. Number 2 was types of chemical changes, and I classified them based on what? Endo versus exo, based on what? Whether they absorbed or released energy. Right. Third one was reaction tendencies, or forces that drive all these reactions. And they were 2. Everything seeks its lowest energy state. Okay, ball rolls downhill. And everything becomes more disordered. Entropy is the other one. Now this is 4 underneath that same title of chemical changes. So we're still doing this stuff. All right. So, and underneath, I want to be able to, I'm impatient, as you can tell. So I want to be able to make my chemical reactions go faster. Now, keeping this in mind, keeping this graph in mind, which is the graph of, which is that, endo or exo? See, right now you can't, it's not like automatic. I understand that. So you think about it. First you think to yourself, well, it starts out up here and it ends up down there. So if the energy is being absorbed or released, if it starts here and it ends there, what must it have been doing that whole time? Releasing, because this kind is absorbing, right? So, if it's releasing energy, this kind is, what would I call him? X. Okay. So, that's how you notice, when I ask the question, most of you just look like, I don't remember. I have to go and look at my notes. I didn't memorize that yet. You don't have to. You have to think about it. You look at the shape of the graph, you figure out if he absorbed or released energy. Once you know that, and exo, exit, expel, you put 2 and 2 together. All right, but here's my point. How can I make it get from point A to point B faster? If it's a ball, what would I do to that ball? Push it over the hill. What's that equivalent to? In this case, adding what? Adding what? Energy. I give them a push over the hill. I add some energy. Exactly. And that's the first way I can increase the rate of a reaction, add energy. And that's why when you did that lab just a few minutes ago, in 2 cases, you had to add energy. In one in particular. It doesn't mean it has to be a chemical reaction. But certainly in the first one, I hope everyone recognized that one, where we took magnesium, we put it into a flame, and we caught it on fire. I think most everybody realized that we were raising the temperature of that magnesium until it got to the point where it went over the hill all by itself, and it was a spontaneous chemical reaction. Okay, so that's one way. Light. Where do we use light? What particular reaction uses light to be able to get its reaction going? Photosynthesis, sure. And electricity and stirring. I could use all of these, and we do use all of these, and we will use all of these all year long. Okay, I'm going to decompose water with electricity, and you're going to stir things up in pretty much every lab. All right, what's another way I can make a reaction happen faster? Think about it. What else would you do to something if you wanted to react faster? What else? How else could you do it? Somebody come up with this next one. It's something your bodies have also. What? Catalyst. That's actually, don't write that one down. I'm going to say that one for last. Absolutely, catalyst. What are your bodies made mostly of? Water. Dissolving things in water actually makes a reaction go faster. Did you notice that most of the stuff we have back there was dissolved in water? It was dissolved in solution. Okay? Every chemical back there, with the exception of the calcium carbonate, was a liquid. Now, most of you guys are thinking, yeah, that's a liquid, right? Okay, so like silver nitrate's a liquid. No, silver nitrate's not a liquid. Silver nitrate's a solid. Okay, silver nitrate is a solid. It's a solid dissolved in water the same way salt is dissolved in water in the saltwater solution you use. Okay? It's the same thing. It doesn't mean that salt itself. You all know salt is not a liquid. Most of the things we did back there are solutions. Your bodies take advantage of this. Your bodies take advantage of this too. You're a warm-blooded animal. Warmer temperature of your body allows you to carry out reactions faster, okay, and do things that have more energy. Okay? A snake, a cold-blooded animal, it's going to not have as much energy, not have as much when it's cold outside, right? Okay? All right. Another thing you can do, and this one, see if you can tell me what it is. I'm going to give you a hint here. You're going to use, I didn't use it yet, but you're going to use the mortar and pestle. Remember the mortar and pestle, what it looked like? I'll crush things up with it. What will I be increasing there when I crush up the substance, whatever I'm going to crush up with it? What am I increasing? The what? 2 words. Nobody? Somebody got it in the last class. Surprise. Surface area. You ever hear surface area? Yeah? Okay. So increasing the surface area is another way to make the reaction go faster. You see, in order for a reaction to happen, you're going to learn when we get to kinetics in Chem 2. In order for a reaction to happen, molecules, atoms, ions, whatever they are, have to hit. Now, if I've got a big chunk of it, like I've got a big chunk of sugar, just a cube of it, and I throw it just dissolve it in water, it's going to take a lot longer, right? But if I crush it up, it's going to be a lot faster to react. It's going to react a lot quicker. Now, in fact, so much so, it's kind of impressive when you see it. I have a little video clip here. If you turn that light off, it's kind of impressive when you see the difference between when you, oops, sorry. Uh-oh. Don't tell me to quit on me. Get the, hold on. All right, there we go. All right. Well, this is going to work. It's not frozen. All right, I just found this little clip. I actually bought the kit to do this, but it only works about once every 10 times. It's very difficult to get to work.
Thursday means it is time for Imagination Station. They are visiting us.
All right, now he's got some powder there, right? And it's
Get
flammable.
your goggles on, just the goggles.
Just the goggles this time.
Okay.
Safety first.
Yep. And I want you to take this lighter, light it, and go ahead and
That's a
touch it to my
flammable powder. Put some match on it. He was all scared.
Nothing's really happening.
But
right?
nothing happens.
I know, Chris. But
I'll talk while he's talking, all right? So I touched that match to that, or that lighter to that pile of powder. It's just it could be any kind of powder, talcum powder, whatever. It's like coating powder, or whatever he calls it. And it doesn't catch on fire. However, if you watch what he's about to do here,
first,
okay.
Hold it out in front of you, tilt it towards me a little bit, and just hold it down.
Okay.
All right. So go ahead, give it a light.
Same
and I'm going to go ahead
stuff.
and put this right through the air. And now that it's surrounded by more oxygen, we're able to get a lot more of that combustion reaction.
Which is
Kind
pretty
of cool.
I like it.
But
Yes.
the
very
demo
cool. So this is actually kind of a big worry.
that he's going to do is kind of cool. See these
Kind of like out in the
paint cans? I mean, I bought this kit. I've tried to do this, and I think I got it to work actually once. It's a real pain in the neck. That's why I was going to show it to you. You're going to do the same basic idea. He's going to take that same powder inside of there in a funnel, and you're going to squirt some air in it so it vaporizes, not vaporizes, but makes an aerosol out of it, makes it airborne, and a lot of surface area when he squeezes that. I also have a little candle in there. All right, and what happens, as you'll see, is what happens sometimes what's called a grain elevator explosion. All right, let me get to the back. Okay, you ready?
Are you ready? Don't do it yet. Go ahead.
All right, and that actually happens.
Excellent.
People have actually been killed by grain elevator explosions. Oh, and a lot of other places too. Like if you're on a farm and you have, like I say, a grain elevator is just a storage place for different kinds of grains, maybe wheat or corn or whatever. And when you dump all this stuff in there on a dry day, it makes a lot of dust. Sawmills have to worry about this too. Okay, it makes a lot of dust in the air. One little spark, and what happened to that paint can is what will happen to the whole building. All right, it will blow up. All right, because of the surface area being increased so much. So we've got 3 ways so far we've talked about: adding energy, heat, light, electricity, stir it up, dissolving stuff in water, and increasing the surface area. The next one, which someone mentioned, I think that's usually the second one people come up with, is a catalyst. let's talk about a catalyst. I actually have a little demo for you for this catalyst. Now, first of all, you'll notice something about a catalyst. It speeds up the reaction rate without actually being used up. That's important too. A little bit of catalyst goes a long way because you don't actually use it up in the process. Your bodies have lots of catalysts. What do we call biological catalysts? Who knows? What's that?
Water.
No. What's that?
Enzyme.
Enzymes. Yeah, enzymes. Now, there are different kinds of enzymes, and that may be one of them. And all enzymes are proteins. But enzymes are the biological catalysts. And your body couldn't do what it does without enzymes. Even though you are warm, and even though most of your chemicals are dissolved in water, you couldn't do it without these guys. Because what you're doing right now is burning sugar. Remember when we burned sugar in the very first demo I did? I took it, I put it in a flame, in a test tube. Caught on fire, smelled like burnt marshmallows. Remember, walked up and down the aisles? Well, I had to get that sugar really hot to do that. You guys are doing exactly the same thing. Exactly the same products are being given off. All right, when I burned sugar, I took oxygen in the air, and I combined it with the sugar, and I got carbon dioxide and water. You saw the water, you saw the carbon. All right, it was carbon dioxide as well. You guys are doing the same thing. You're breathing out carbon dioxide, you're breathing out water, all right, and you're taking in oxygen, and you're burning it, but you're doing it at a much lower temperature because you've got catalysts, you've got enzymes. Here's how a catalyst works. This guy up here, and I get this as a mistake all the time, this guy up here works completely different. Adding energy is not the same as adding a catalyst. Not at all. Let's go back to my little graph here. Again, you don't have to copy this, just watch. Here's what adding energy is equivalent to. Pushing a ball over a hill to get him, and I don't care how big the hill is. I don't care if it's an endothermic or an exothermic. Heating him up is the equivalent of pushing him over the hill. For a catalyst, it's the equivalent of finding a way around the hill. Finding a different path for it to take to get from point A to point B. All right? That's what a catalyst does. It lowers that hill. What is that hill called? Remember? Look back. What is it called? The activation energy. That's what a catalyst does. It lowers the activation energy so that a reaction is going to happen a lot faster. It means less energy is needed for this reaction to occur. I can make this paper burn by putting it in an oven and raising its temperature up until it spontaneously combusts. But I can also add catalysts to things to get the same thing to happen, like I'm going to do for this hydrogen peroxide, all right, as a demo. All right, I want you to watch this. This is a pretty neat demo. It's a classic demo. I'm going to take some hydrogen peroxide, which, by the way, is always decomposing. And here's what it's decomposing into. Hydrogen peroxide looks like this. You don't need to write it. But, oh, wait, one more little analogy to this. Kind of like, you've all been through the Allentown Tunnel, right? You see that big mountain in front of you, and you go right underneath it. You know, if you're going through the tunnel or if you went over the mountain, you still end up in the same place. You still end up in Allentown. But it takes less gas. It takes less energy. It takes less time to get from here to here because you went through the tunnel. And that's why catalysts work. It makes the reaction happen faster because it doesn't take as much energy to get there. All right? Nothing in its way. At least not as big of a thing in its way. When we get to kinetics, the chapter, you'll learn how that happens. Sometimes it'll form different intermediates. It'll have a different pathway to go. Sometimes it just gives it a surface upon which it can happen. Like the catalytic converter in your car. Catalyst, catalytic converter, right? You may have heard of that. Okay, hit that light for me. I'm actually going to put both of them on, please. I'm going to do the opposite again. I'm actually going to put gloves on for this because I don't really want to touch this stuff without it. I don't have you guys wear gloves very often because most of the stuff we use back there isn't very dangerous. You say, well, geez, it's only hydrogen peroxide, so what's the problem with that? Don't you guys have hydrogen peroxide in your house? What do you use it for? Yeah, you put it on cuts. What does it do when you put it on a cut? Burns. Yeah, and it also does what? Yeah, it cleans it out because it You ever notice? It bubbles. It fizzles. Okay. Well, if you've got an old bottle of hydrogen peroxide in your house, you probably have an old bottle of water, because hydrogen peroxide right now is sitting here in front of me. Okay? Just sitting there. It's decomposing. It's doing this right now. Decomposing. And I'll explain why, when I'm done, I'll explain why this bottle looks the way it does. It's kind of like an accordion. Hydrogen peroxide, turn that light off for a second, is right now in front of your eyes, H2O2, that's what this is, H2O2, is becoming water and oxygen. And so if you have a bottle that's very old of hydrogen peroxide and maybe has been stored in a warm place, especially if it was stored in a clear bottle, you probably have a bottle of water, all right? Because it probably already converted into water and oxygen. The oxygen given off is a gas. I told you I'd talk about this. Oxygen's a gas. Why do you think this is an accordion? Yeah, so it can expand. If you have a glass bottle of hydrogen peroxide, you must be very old, because they shouldn't sell it in glass. It should be in plastic, because it would crack because of the pressure that could build up. All right, light back on. Now, I'm going to add a little bit of soap to this. You watch it? So you can see it a little bit better. But right now, in front of your eyes, this stuff is changing into water and oxygen. Stir it up a little bit. Okay? Now, I'm going to add a catalyst to it. I'm going to take away that hill, or at least I'm going to lower it. It's not going to be as hot. So when I add this catalyst, sodium iodide, to this, let's see what happens. See if the same reaction is going to occur. Okay. You ready? There you go. But it's happening a little faster now. May have added a little bit too much there. It's alive. And you notice this coming off the top here? What is that? It's not smoke. It's just steam. It's actually steam. Yeah, the bubbles here. It's really hot. It's another reason I have gloves on. Right? Because that's really, really warm. Even to touch it with gloves is pretty warm. All right. Same thing, same reaction, but it would take years for all of that to decompose just sitting out in your counter, in your cupboard. But it all happened in a matter of seconds because I took away the hill. I made it. Now, I will get as a mistake. Every year I get as a mistake. Light back off, front light. Every year I get as a mistake. Catalyst. Oh, that's good. That's not going to help. Don't use this glove. I think I'm throwing that one out. Every year I get as a mistake. Catalysts push him over the hill. Catalysts do not push him over the hill. You guys push me over the hill. But catalysts do not push him over the hill. They lower the hill. By the way, before I erase this, is that balanced? No. And that's when we learn about balancing equations. We'll learn how you're going to balance that. It's really not that hard. You probably could do it right now, but we're not talking about balancing equations right now. All right. So, final thing about catalysts, I already mentioned it, but I'll say it again. Enzymes are your biological name for a catalyst. And it's the reason why you're able to do what you're able to do, burn sugar, without being 400 degrees. Just 98.6. All right? Know the difference between these. On the test, I can ask this question in multiple ways, including a longer question about catalysts. All right. And I'll talk about, by the way, I have a little bit more notes to give you. These are going to be very quick notes. But tomorrow, if you're not here tomorrow, you really want to watch that video because it's going to talk about the test. This is your first test you've had from me. I'm going to hold the test up off camera. But I'm going to hold the test up and show you and read every section off to you. You're going to know exactly what's on the test. Like I told you at the beginning of the year, no one ever complains about the tests or me being unfair. All right, you'll know exactly what's on this test before you get it on Friday. All right, let's get the last of the notes here first, though. I saved this for last because it really is. We've been talking for over a week now about physical versus chemical changes. This is really has not really a lot to do with that. It's more back to classification of matter. But remember, the title of this chapter is Matter, Energy, and its Changes. We spent most of the time on the changes, physical versus chemical. But a little bit about matter now. We also talked a little bit about conservation of matter and energy, law of conservation of matter and energy. Can't create or destroy matter. Can't create or destroy energy. Can just change form, Einstein, right? Well, this is stuff I saved for last because it's so easy. I'm going to fill up this one board, but you've seen it all before in probably elementary school, but certainly middle school. How do we classify all of matter? 3 categories. Things on the periodic table, what are they called? Elements. Put 2 elements together. What do you get? Compound. Compounds and elements mixed together, what do you get? Mixed together. Mixture, yeah, exactly. All right, so those are the 3 things. First of all, what is matter? Nothing. What's the matter with you? Matter is anything that has mass and takes up space. And I actually use this as an example. I always do this at this point to remind me that so I actually get people who still, in high school, get really bad answers on this. Like people who say, if I had you classify something, matter versus energy on a test. I can still get people who say air is not matter. Air is matter. You can't see it, but that doesn't mean it's not matter. Air is absolutely matter. Air has mass, and it takes up space. It takes up space in the balloon, and it has mass. If you don't think it has mass, why are we afraid of hurricanes? It's just a bunch of wind, a bunch of air being moved around, but it can knock over a house because air has mass. A lot of it. Okay? So anything that has mass and takes up space, all right, what would not be matter then? What would be an example of something that's not matter? No. I can think of something that's not matter. Think. Like poop. Think. What are you going to say? What? You said something. Poop? No. Think. Light would not be matter. Exactly. Light doesn't have mass. Who said that? Right. Light has light. Electricity. Heat. Energy, basically, right? Energy. Okay? These things do not have mass. I mean, they don't take up space, all right? But anyway, back to our classification of matter. Let's do elements first. What makes something an element? Well, here, I'll talk about 2 different ways. One is the correct answer. 2 is, what do you care about it for the test? Well, you care about it for the test, so do that first. It's a cheat sheet. You all have the biggest cheat sheet in the world. It's right there on that wall. It's the periodic table. I cannot create an element. I can't make up a new element. If I ask you a guy up there, and you see him up there, and he's on the test, you know he's an element. Now, you don't have to memorize that periodic table. And I'm not going to ask you some crazy guy like tellurium or antimony or technetium. I'm going to ask you guys that you've heard of, like aluminum or carbon or oxygen or whatever. Something you've heard of. If it's there, it's an element, very simple. But what is an element? All right, what makes something an element? Well, turns out it's the smallest unit of a substance that maintains its own unique properties. I need to explain that after you're writing it down, or as you're writing it. There are smaller things than atoms. There are smaller things than elements. What's something that makes up an atom or makes up an element? What makes up an atom? Protons, neutrons, electrons, and there are smaller things than that, like quarks and hadrons and leptons and pions, and I don't even know how to pronounce half of them. There's all kinds of small stuff like that, right? But a proton in a carbon atom is the same as a proton in an oxygen atom. And it's the same as a proton in a chlorine atom. But a chlorine atom is different from an oxygen atom. It's different from a carbon atom. So the smallest thing that is still unique to itself has its own unique properties. That's what an element is. And you can find them all on the periodic table. There's no hiding them. I can't cheat you here. I can't trick you here. And you all have a cheat sheet. So that's easy enough. Let's talk about the next guy. Which would be what again? Compound. All right, how about a compound? A compound is going to take elements, 2 or more of them, and put them together. But not just in any old way. It has to be put together chemically. Let me show you the difference here. Can you think of a chemical combination of two or more elements? You think of one you're familiar with. Water. What's water made out of? Two hydrogens and an oxygen. So a hydrogen and oxygen are combined together chemically. A chemical combination of two or more elements. Absolutely. All right? Can I have hydrogen and oxygen mixed together? Sure. There's probably a little bit of hydrogen in this room. There's certainly a lot of oxygen. Okay? But unless, there's not a whole lot of hydrogen, luckily, or we'd be blowing up. If a little spark. But my point is, there's a difference between a mixture and a compound. The compound, when you chemically combine these two things, it's not like with a mixture. You actually can't separate them back out. They have brand new, unique properties. Okay? Water has both hydrogen and oxygen, yet I can't breathe it. Let's think about the two things I could do with hydrogen and oxygen separately. These are the four guys, by the way, I would expect you to know. I am not going to ask you, some complicated organic formula, whether it's a compound, and with just a common name for it, whether it's a compound or an element. I'm going to ask you these four guys, because they're the only four you know how to name so far. They're the only four you know how to write the formulas for. So they're the only ones you're going to see on this test. You understand? No one has to worry about me asking you what the formula for acetaminophen is, or aspirin, or if that's a compound or an element. It will be one of these four. Water, CO2, NaCl, or sugar, which is glucose. Other names for sugar, glucose, sucrose, sugar, C6H12O6. Okay? All right. Here's the difference. Take a look. They're chemically combined because what can I breathe oxygen, correct? Can I breathe water? Totally different properties. Hydrogen. That was in the Hindenburg. You ever hear of the Hindenburg?
Yeah.
Big Zeppelin that blew up? So hydrogen burns. Can I burn water? Nope. Water it's completely different. It loses its unique properties when H gets together with O. I can no longer breathe oxygen. I can no longer light water on fire because hydrogen is combined now differently. The final one, mixture, they do keep their unique properties in a mixture. It's a physical combination only, not chemical. And they do keep their unique properties. And I'll give you an example of that after you copy it down. If it seems like I'm going fast through this, it's because I am. Because all of this stuff you've heard before. Nothing in here is new, really. And even if it were, it's not very difficult. Let's relate this back to the lab you guys did on Friday. A mixture, physical combination of two or more substances. Okay? Remember what I did in that lab? Remember what you had in that beaker, that plastic beaker? You had sand, sugar, salt, iron filings, marbles of different color and size, right? You were able to separate that mixture out strictly by physical means. What were the physical properties you used to separate them? Solubility, dissolving them in water, right? Magnetism, color, this one's black, this one's clear. Size, all physical properties, all physical means, able to separate that. Can I separate water into H and O by physical properties? No. They're stuck together, they're chemically combined, cannot separate them except through a chemical process. All right, last thing I'm going to do with mixtures, maybe something you haven't seen, but I know you've heard the words before. I can classify my mixtures into two different kinds, homogeneous and heterogeneous. You've heard that word before. Homogeneous, what? I was thinking of, you'd say milk. You ever see on your bottles of milk it says homogeneous? No? Everybody knows that? In genetics, you've heard the term homo and hetero as well. For what? Homozygous and heterozygous. Remember that? Let's do a little refresher, even though you guys all passed your keystone. Remember doing those kind of crosses, right? What would I call this guy? Homozygous dominant. What would that guy be called? Heterozygous. And this guy? Homozygous recessive. Good. A little bit of a review here. Homo means same. Same. Homozygous dominant, homozygous recessive. Homo means same. Hetero means different. Okay, and how you apply that to a mixture? Very simple. If the mixture is the same throughout, or basically the same throughout, like the air you're breathing right now, we're lucky that it is about 20% oxygen and the rest of it's mostly nitrogen. If we didn't have that same percentage throughout, all right, you know, if one breath you took it didn't have any oxygen in it, the next one took it had a lot, all right, you'd be in trouble. Okay, that's a homogeneous solution. So would salt water be? I put my salt, I put sugar in water, I take a drink of it. I don't want to drink salt water, but I take a drink of my sugar, my coffee, my tea. Tastes the same every cup. As long as I don't add so much it's sitting on the bottom, it's going to taste the same. All right, that's homogeneous. Heterogeneous, that's different throughout. It's not going to be the same throughout. All right, an example of that would be, well, pretty much anything that was alive or is alive, you are heterogeneous. Every part of you is not the same as every other part. All right, a rock is not homogeneous. Different parts, different stuff in it. And you'll see some examples of that in the homework tonight, as well as in the worksheet I'm going to give you. Let's look at the homework. Kind of copy this down. Oh, by the way, one last thing before the homework. So here's how you would classify all of that. You don't have to copy this. Just look. You have mixtures, which can be homogeneous. And by the way, brass is just a mixture of copper and zinc. And heterogeneous, all right, where I've got, look at water and some pennies in there. That's not the same throughout. But I've got elements like copper and compounds like water. So I put water and copper together, I get heterogeneous mixture. And here's your homework right at the bottom there. Did y'all copy that? Okay. Tomorrow's a review. If you're not going to be here tomorrow, make sure you watch it. I'll talk a lot about the actual way I'm going to ask the